a long heat generating wall, a long heat generating wall, a long heat generating wall is bathed, not baked. A long heat generating wall is bathed by a cold fluid. A long heat generating wall is bathed by a cold fluid on both sides. The thickness of the wall is 10 centimeter. Long heat generating wall is bathed by a cold fluid on both sides. The thickness of the wall is 10 centimeter and the thermal conductivity of the wall material, and the thermal conductivity of the wall material K, the thermal conductivity of the wall material K is 45 watts per meter per Kelvin. K is equal to 45, thickness is 10 centimeter. The temperature of the cold fluid is 30 degrees Celsius. The temperature of the cold fluid is 30 degrees Celsius. Thermocouples located inside the wall. Thermocouples located inside the wall. Thermocouples located inside the wall show the following temperatures. Thermocouples located inside the wall show the following temperatures. Okay. So this is the wall. So the thickness is 10 centimeter. K is 45 watt per meter per Kelvin. So on both sides it is bathed by a cold fluid. I do not know what is H. So this infinity is just a depiction to show that it is infinitely long. Okay, you have taken down all the data. The problem continues. The temperature distribution is symmetric above the midplane. The temperature distribution is symmetric about the midplane, and the origin is indicated in the figure. The temperature distribution is symmetric about the midplane and the origin is indicated in the figure. Okay, that the temperature distribution is symmetric is consequent upon the fact that there is uniform volumetric heat generation. Okay, we will come to that a little later. Using a second order Lagrange interpolation formula, find H at the surface. Using a second order Lagrange interpolation formula, find H at the surface. If the cross sectional area of the wall is 1 meter square, that means okay, I am talking about this area. if the cross sectional area of the wall is 1 meter square, determine the volumetric heat generation rate, determine the volumetric heat generation rate, determine the volumetric heat generation rate in the wall for steady state conditions, in the wall for steady state conditions. Just think about this problem. Huh? No. No. No, the temperature distribution is like this. Cross sectional area is like this, right? No, but this. No, that infinity is basically in order to make it tractable I am giving 1 meter square. What you are saying is correct. When it is infinity I am saying with respect to 10 centimeter it is. Alright. No, he has a point, but without 1 meter square I cannot proceed. Okay. If you want I can, if you want me to remove this I can remove. Okay. Now which is the cross sectional area? That is fine. Okay. Now just think about the problem. What is it we are trying to do here?
Expression for t as a function of x.
You have to get t as a function of x. Okay, and then do what? Yeah, q is equal to k times dt by dx. This q which is coming from the wall is the conduction. That which is going from the wall to the fluid is convection. I already told you it is steady state. So whatever heat is coming from left to right through the wall has to go out. Therefore this q conduction is equal to q convection. Now you can say, sir, straight away I can, why go through this pain? Can't I keep thermocouples here and all that? It will disturb the flow and all that. It may make a laminar flow turbulent and all that. We do that using hot wire anemometer. You can directly get some, but the boundary layer is so thin that it is very difficult to do those measurements. Therefore we would much rather prefer to do the measurements on the wall where it is easy to put thermocouples, and then using the conduction convection coupling we just make use of the fact that q conduction here will be equal to, here it is q conduction, here it is q convection, and determine the heat transfer coefficient. So this is one way of determining the heat transfer coefficient. Okay, so I pose it, this is typically what is called as the inverse problem. I have a mathematical model for this. The mathematical model for this is d square t by dx square plus qv by k equal to 0. I have a mathematical model for this. I have some measurements of temperature, that is I have x0, x1, x2. Okay. So I have a mathematical model, I have some measurements of temperature. So if I marry this mathematical model with these measurements, I am able to get much more information about the system. What is the information I am getting? I am getting two more parameters. I am able to get the heat transfer coefficient, at the same time I am able to get the volumetric heat generation rate. The straight problem would be very simple. What you learn in ME 317, that is a basic heat transfer course, will be there is a wall which is conducting and there is a convection at the boundary. Heat transfer coefficient is given to be 250 watts per meter square Kelvin. It generates, there is a volumetric heat generation of 10 to the power of 5 watts per meter per Kelvin. What is the surface temperature? What is the temperature 1 millimeter away from the surface or 1 centimeter away from whatever? Okay, so this will be the, so that will be the straight problem. Now we are making some measurements and we are inferring some properties of the system. So this is what is typically called a inverse problem. Okay, fine. Now I gave it as 10 centimeter, I hope. So one is here, 0. What is this? Okay, so one is already at the center, right? Okay. But I gave you 4, so now we are having a problem. You have to choose 3, right, for the Lagrange. Which 3 did you decide?
Last 3.
choose something which is closest to the wall, right. So no, I have no problem, you can choose the other one also, right. Okay. So don't look at what I am writing on the board, you do parallel processing, then towards the end you can exchange notes, you can look at the board and see whether what I am doing is alright, you just proceed. Now okay. I want dt by dx where at x naught, right. So first we will put dt by dx, let us not try to do, let us not try to combine too many steps, correct. So I just took the dt by dx, you can substitute for all the values of x. So dt by dx both are plus, right, minus into minus, is it okay, yeah, multiplied by x2 minus x0, is it right? Did I make any mistake? Is it all right? Akshay, is it okay? So, Sampath, what is dt by dx at x0?
I took different one. I took the last three, second, third and fourth.
What is dt by dx at x0?
23.33.
23. It will be very large, right?
21,566.
Is it?
15 centimeters.
No, the first is minus, right? The first is minus, the second is plus, the third is minus. 233, correct, 233.33, yes. What are the units? Kelvin per meter, correct? What degree Celsius? Yeah, please. What is bothering you? One degree Celsius is equal to 1 Kelvin if you are talking about differences in temperature, correct? All right. So now how is it going, the temperature? It's going like this, okay. So in which way is the heat flowing? Like this, okay. So it is in the x is in which direction for us? Therefore we have to adjust this, 80 minus 30, 50. So h equal to what did you get? You got something different? But is it so? It cannot be way off. By? Percent?
This is no, not percent. The value. This is 209.
209?
209 points. 210.
Other one? So what was the value of the gradient? You got 233.3. See, when you do all this complicated stuff, okay, you are taking 0.01, 0.03 minus, plus and all this, and there is a possibility that you can get lost, okay. But back to basics is very important. If you took a very desi approach, you will take only 2 temperatures and divide it by delta x. So 2.1 divided by 0.1, it's around, what is the gradient? 210. So this is a ballpark value, so you should get of the same order. If here you get 200, here you get 900, something has cubbed here, some minus you put as plus, or if suppose you get 23,600 or something, then you should, then you know that it is always in Lagrange, one will be minus, one will be plus. You have to be extremely careful, you have to tread with caution. Okay, now what is the last part of the story? How do we get the volumetric heat generation rate? What? You can go to the equation, but there are several ways of doing it. What is the heat transfer from the right side? HA delta T. What is the heat transfer from the left side? HA delta T. Total heat transfer is 2 HA delta T. Where is all the heat coming from? Heat generated per work. So QV, so many watts per meter cube into 1 meter square into 0.1. So the QV into volume must be equal to 2 HA delta T. There you are. Then you get QV equal to, then get the value. So it should be the order of 10 to the power of 5 watts per meter cube. This is without taking recourse to the equation. The equation is d squared T by dx squared plus QV by K is equal to 0. It is a very threateningly formal way of stating the energy balance, right? Is it okay? Nishan? Anish, you got it?
Yes, sir. I'm trying to repeat it.
Try to?
I'm trying to recreate it.
Yeah, okay.
So these three temperatures,
Uh.
and like while taking the wall temperature, can I directly use this? Or
What?
should I again, as in no, the convection we use this temperature, wall temperature, right? Can I use this or should I again find out?
No, but if you do this, you are not getting the gradient at the wall. You have to get dt by dx. So you should have used these three temperatures at least. You should have used at least 0. See, when you are taking 3 temperatures, you could have taken any 3 out of the 4. But 0, 80 degree centigrade is very crucial because you are evaluating the gradient there. For example, what Sampath has done is, anyway Lagrange interpolation second order 3 points. So he has taken 0.01, 0.03, 0.05. But with these three, you can't get the gradient at 0. Gradient at 0 is what matters because k dt by dx at x equal to 0 is the heat transferred by convection. You could have taken this or this or this, but as you go away and away from the wall, because of nonlinear effects, is more error prone. Okay, so using overall energy balance. Thickness we will call it as L. Is it okay? Huh? 8.5 into? That's all. Ah, 2.1 into? Did I make a mistake here? All right. So there is a heat generating wall. There is a heat generating wall which has a thickness of 10 centimeter, whose thermal conductivity is given by 45 watts per meter per Kelvin, and the heat generation rate is estimated to be 2.1 into 10 to the 5 watts per meter cube. Now it is possible for you to apply the knowledge of heat transfer and get the maximum temperature, and you can turn around and see whether that temperature is the same as what is measured at 0.05, right? Yeah, so what is the governing equation? because it is symmetric at the center, right. With these two boundary conditions you can solve for A and B, then you can get the temperature. This is an additional check. So this is a very simple presentation of inverse heat transfer. So I surreptitiously taught you inverse heat transfer, though the original intent is to teach you Lagrange interpolation formula. This inverse heat transfer can be very powerful. For example, last year when people were in the international terminal, when people are arriving, they were taking thermal infrared image. Okay, it is basically they are working out an inverse problem, right. So when they find that the radiation from the nose and the certain parts exceeds a certain value, then he is having fever, then it could be swine flu. And okay, for example, thermal infrared, for example, for breast cancer detection, if you can use an infrared camera and get an image. Now if there is a tumor inside the breast, the metabolism will be high. If the metabolism is high, that means it's watts per meter cube, the volumetric heat generation will be high corresponding to the tissue which is non-cancerous. Therefore this will show as a signature on the surface temperature of the breast. So this is called a breast thermogram. Now from the temperature on the breast, if on the surface of the breast, if you can solve these equations, that is you assume the location of the tumor and the so many watts per meter cube, for different scenarios you can recreate what will be the temperature on the surface, then find out which matches with that which is measured, then you can get the exact location and size. Like that you can do for several, you can use additional things. So the computerized axial tomography, the CAT or the CT scan basically works like this. It tries to create 3-dimensional views by taking repeatedly 2D views in several angles. And so what is running behind, what is the engine behind all these CT scan? There is a powerful optimization program which is working. Okay, so medicine is more or less, orthopedics is mostly mechanical engineering now. They put plates, this thing, nuts, bolts, everything, they do lots of orthopedics is engineering now almost. So there is a journal of engineering in medicine, right, lot of orthopedic doctors, journal of engineering in medicine. Orthopedics doctors have also got PhD in engineering nowadays. There are some in Madras, Apollo Hospital, who have their super specialization orthopedic surgery. They also have a degree in, they also have a PhD in engineering. Okay, so now was there someone who got the value of T at the center? Huh? How to get the second derivative with the Lagrange interpolation? For example, I will denote a general variable phi or phi instead of t. It could mean any variable. Now you can write out the Lagrange formula, you can take dt by dx. Now you got dt by dx, right, like that you have to get d phi by dx. Can you get d squared phi by dx squared, right? So the first derivative, two by, correct. Okay, so what is the big deal? Let us consider the Laplace equation. Okay, the Laplace equation is del squared phi, where the del square is called the Laplacian operator. Okay, d square t by dx square plus d square t by dy square equal to 0. Okay, let us consider okay. I consider this as point P, I consider this as point east, this as west, this as north, this is south. If so, this is x and this is y. If delta x equal to delta y, using Lagrange interpolating formula, it is possible for you to get the second derivative and write the second derivative at P in terms of the values at east and west, if you are considering d squared phi by d squared phi by dx squared. By the same token, it is possible for you to write the second derivative at P, that is d squared phi by dy squared in terms of north and south. If you simplify, you will get an amazing result. Please do that. You will get an amazing result if delta x equal to delta y. See, this cannot be straight away. This d squared phi by dx square is the same at all the 3 points. It is not a function of x, isn't it? Correct. So, what does it mean? For example, I should have you got to reduce this, you got to reduce it to that form. Okay, will you do that? So, this will be delta x, watch this. So, this will be delta x, this will be, this will not be delta x, please correct me, minus delta x. So, this will be minus delta x, this will be minus 2 delta x, this will be delta x minus delta x. But this fellow already has a 2 here, this fellow already has a 2 here, these fellows have a 2 in the denominator, this fellow does not have a 2 in the denominator, therefore this fellow will get multiplied twice. So, that is the node under consideration. Okay. Similarly, is it too fast? Is it going beyond your head or above your head? No, fine, right? Huh? Difficult? Huh? Oh, Why why didn't you get d square phi by dx square at the center using the Lagrange? Can you write the Lagrange polynomial in terms of x? And then can you get the first derivative and second derivative at p? Yeah, that will be this. The second derivative anyway is not a function of x, so whatever you have written is applicable, except that this is 1 2, right? Why did you write 2 3? I wrote 1 2 3, okay. No, but this is not consistent with this. No, we'll change. Deepak, you got it now? What is bothering you? What is the? I am trying to evaluate the partial derivative using the Lagrange method. Which one?
For writing it as a difference, shouldn't it be an ordinary?
No. We are with the understanding that we are looking at the derivative in the x direction. It's all right. It's perfectly okay. There is no problem. Now, if you do this, so what I am trying to do is I am trying to write out the second derivative using the Lagrange interpolation formula. Now, if I do this, what is this? When you write like this, what is it known as? This comes from where? Finite volume. So this is called the finite volume. Of course, you can say no, yeast is what? What is this? This is finite difference. Okay. So, the Lagrange interpolation formula can be used to get the finite difference and finite volume representation of partial derivatives also. Okay. More importantly, when you are solving for a, have you taken this down? Very good question. So, this basically the finite volume, though the end result looks to be the same, the process by which we do this is completely different. In a finite volume method, we actually integrate the equation and you conserve the mass momentum, and and finally it turns out like this. But this fellow we break the derivative. dt by dx is ti plus 1 minus ti plus 1 j minus tij divided by delta x. So eventually it may lead to the same this thing, but it leads to the same result eventually because we did so many things, delta x equal to delta y and this thing. So finite volume is basically a conservative scheme. It conserves mass, this thing. Finite difference, basically finite difference works on Taylor series approximation. You cut it off after a certain number of terms. This basically integrate. Finite volume method, you can, if you more you can actually work further and develop what is called the finite element method. Even there you integrate the governing equation once. When you integrate the governing equations, all the partial differential equations, it will be conservation of fluxes, correct. What is this u dou E by dou x after all? dou by dou x of E square into half, and you can apply the continuity equation. You can write the whole thing in terms. You have not learned boundary theory and Navier-Stokes equation. So okay, so you can rewrite all that, and you integrate the governing equation once, and then you will get the finite volume and the finite element representation. So to cut a long story short, from the Lagrange interpolation formula, it is possible for you to proceed to solution of partial differential equations. Okay, so even this you can set up a scheme. You can set up a scheme where I also have a east, west, north, south neighbor for the next fellow. Then I ask you to set up 4 equations using the Gauss-Seidel method. You can keep on iterating. You start with some initial guess values and you keep on iterating. This fellow depends on these 4 fellows, this fellow depends on these 4 fellows, and so on. Okay, but the beauty of this is mathematically from the method of characteristics, you know that this is what is known as a elliptic equation in mathematics. An elliptic equation requires information from all sides for it to be mathematically closed, so that you can solve it. A parabolic equation is one in which the information does not flow downstream. It is typically like this, the parabola is like this, so the information does not flow downstream. So an initial value problem, you start with an initial concentration, initial temperature, how this marches in time. You do not worry about, you do not go backwards in time. That is a parabolic equation. So you do not require information from so you march ahead in time. Similarly, in an elliptic equation you require information from all the boundaries. So information, so here it is symbolized by that the nodal value at P is dependent on east, west, north, and south. So to round off the discussion, for example, if you have a boundary layer which is developing like this and you want to measure the temperature or something, so you can take your anemometer and get points and get the temperature at 3 points, x0, x1 and x2. Using second order Lagrange interpolation formula, you can get a better estimate of the gradient rather than taking x0 and x1 and taking dt by dx1 by taking t1 minus t0 divided by x1 minus x0. Okay, so this can be used for post processing, or you are doing fluent calculations from the temperature and the velocity fields obtained. You don't have to believe the values of heat transfer which is reported by fluent. You can take the raw temperature data, you can use a Lagrange interpolation formula and use a second order or a cubic polynomial and get a revised estimate of the gradients and then the heat transfer rate.